Fermat's principle and Snell's law.
Refraction was explained by assuming that the frequency of the light ray as it passed through different media had to stay constant. The reason for this was if it didn't, then the waves would build up at the interface and they wouldn't go through, and we know that physically that doesn't happen. So when this does happen, we find that the wavelength of the light increases and the speed of the light ray will decrease in a medium with a higher index of refraction. There's another way of looking at this. By using Fermat's principle of least time, which states that light follows a path through different media that takes the least time. This is based on Huygens' wave theory of light, which will be covered in the next section, and even though it was come up with in the year 1662, a similar formalism was used in the quantum electrodynamics description of light and matter in the 20th century. We're going to use an analogy to illustrate Fermat's principle. We're going to start off with a beach over here, and there's going to be a person here, and here's a lake, and here's a boat. And the person can run on the beach. In 10 minutes he can do a mile, and in 30 minutes he could do a mile swimming. So clearly he's a lot faster on the shore. The analogy here is over here, this would be light traveling in a vacuum or in the air, and this would be light traveling through glass, for example. So the question is, which path would get you from the beach to the boat in the shortest period of time? We're going to consider three paths to get from the beach, where the person's standing over here, to the boat here in the lake. One would be the most obvious, just head straight for the boat, okay? Another would be, let's say the runner happens to be a physicist and says, you know what, if I take this path along the beach, I can run a lot faster there, and that'll minimize my time through the water. Okay, he's at least thinking in the right direction, but the best way to actually do this is the path of least time. It's the best compromise between speed and distance. Here is certainly the shortest distance, but too much time is spent swimming slowly. Over here, you spend more of your time running, so that's certainly faster, but you're going an extra distance. So the actual best thing to do is kind of somewhere in the middle here, run down, and then jump into the water and go this way. This is called the path of least time. What's very interesting is that light behaves exactly as the person who tried to get from the beach over here to the boat in the water. This light blue area we'll consider the water. See this path here? That's the path of least time, just like we showed for the swimmer. And in this case, we have the index of refraction here is less than the index of refraction over here, so this could be air and this could be glass. The velocity of the light in the air is much greater than the velocity of light in the glass. And earlier when we talked about refraction is when you have a case like that, the light beam will hit the interface, then bend towards the normal to the surface, which is this line right here. So, what we talked about earlier with refraction is also explained by Fermat's principle. There's an equation to describe how much or how little the light bends, and it's called Snell's Law. And it's pretty straightforward. N1 sine theta 1, where N1 is the index of refraction of this medium, theta 1 is this angle here, that's the angle of incidence, equals N2 sine theta 2. Where N2 and theta 2 are the angles in the second material. So what we have is light will bend towards the normal when entering a denser medium, for example air to glass, and light will bend away from the normal when entering a less dense medium. So if we were reversing this light ray and going this way, you can see how it goes from water, which is a denser medium for light, and it will bend away from the normal as it enters the air.
When light enters a medium with a higher index of refraction, it's going from n equal 1 to n greater than 1, the wavelength decreases. The first picture shows the distance between the wave peaks decreasing as the wave changes medium. Hopefully you can see here the distance between those peaks are less than the distances between each one of these. That causes the wave to bend towards the normal line for the frequency to remain constant. The second picture shows us using only rays, right? Incident ray here hits water, which has a higher index of refraction than air, and it bends toward the normal. A nice way of looking at this is, let's say you have a marching band coming and they're marching on grass, and then for some reason there's this huge mud puddle that they have to go through. You can't march as fast in mud as you can on grass. So the first group slow down. The rest of the line is still moving with the original speed. So as this guy goes from here to here, because they're moving faster, the people here in the mud travel a shorter distance. So what does that do to this light ray? Well, it looks like it bends it down right like this. And then finally, when everybody's in the mud, they're all walking here with the same distance between them. All right, that's not how it really works, but it's a good way to remember it perhaps. When light enters a medium with a lower index of refraction, okay, here you go in n greater than 1 to n equal 1, so at the bottom you have a lower index of refraction, the wavelength increases. The wave must bend away from the normal line for the frequency to remain constant. So let's get our marching band again. Here they are marching in the mud. And then when they first hit the grass at this barrier here, the guys who hit the grass start moving quicker. So they're moving up here, and the people in the mud are still a bit slower. And by the time the people over here catch up, we have now spread out the waves, so you have a greater wavelength. And when you take the perpendicular to all those lines, you have this picture here. The refracted ray bends away from the normal line. The relationship between the angle of incidence and the angle of refraction is given by Snell's law. The equation will be taught in later physics courses because it uses trig functions. Qualitatively, though, we should remember light bends towards the normal when entering a medium with a higher index of refraction, and light bends away from the normal when entering a medium with a lower index of refraction.